Okay, we're talking kinetics here. So last time we went over sort of specific orders of reactions. We talked about, let's see here. We talked about first order. We talked about second order, and we talked about zero order reactions. And remember that each of these sort of has what's sometimes referred to as an integrator rate law, for example, kind of a concentration time dependency. Natural log of A equals natural log of A naught minus KT. We also have for second order, 1 over A equals 1 over A naught plus KT. And for zero order, our A is equal to our A naught minus our KT. Remember as well, some of they have half-life equations which go with a natural log of 2 over K. They also have, for each of these sort of equations, you can rearrange them into sort of a best fit line. And again, for example, this one here, natural log of A is equal to minus KT plus the natural log of A naught. That is, again, in the form of y is equal to mx plus b. And again, that gives us our typical graphs that we associate with these different orders. Here, we'd have the natural log of A versus time, and that will yield you a straight line with a negative sloping line, where the slope of that will equal basically the rate constant. Again, this is obviously what we graph on the y, and that is what is going on the x. We can do that for each of these. For second order, it is 1 over the concentration versus time. This actually will give you a positively sloping line. And again, the slope in this case would equal K. And for zero order, it is really the concentration of A versus time, giving you, again, that negative sloping line where it is equal to minus K. So each of these, as we talked about, has sort of a specific integrated rate law. It also has a specific half-life equation that goes with it. As we also talked about, I think we maybe did an example. Sometimes you do need to use the sort of the half-life equation and the integrated rate law together. And usually in that case, you would need to use the half-life equation to find the rate constant. So you can then go into the other equation. We finished up last time talking about sort of energy and exothermic reactions and endothermic and sort of energy diagrams that we talked about. So in an exothermic reaction, if this is energy, our reactants would be higher in energy than our products. And again, energy has to be sort of given off as a result of that to get there. There is a hill that the reactants have to climb that we talked about, which again is that activation energy, which is abbreviated E of A. And again, when we get to the very top of that hill, that is our transition state. That again is the highest point in terms of energy in this reaction. And that is really where we have things that are not so stable because it's really high in energy. That is where we have that transition state complex where we have kind of partially broken bonds, partially made bonds. And again, it usually will kind of proceed kind of down the line a little quicker. Endothermic is a little different. We have sort of the opposite locations of our reactants and products. Our reactants are actually lower in energy than our products in this case. And again, energy is going to kind of be put in for this type of reaction to do that. Here we have our activation energy here. And also, obviously, our transition state. We could also figure out, as we talked about, the delta H of the reaction, again, by taking the difference in energy between our reactants and products. And again, in this particular case, since we calculate delta H is basically the delta H of the products minus the delta H of the reactants. Our products are lower in energy, so we're going to have a smaller number minus a larger number up here. And that is going to yield us what we normally think about in terms of exothermic for delta H, which is a negative value because of that difference. Same thing here. If we calculate our delta H, which would be like between here, again, our reactants, our products, are actually higher in energy. So that's going to be a larger number minus a smaller number, which is our reactants in this case. And that's going to yield you a positive value for delta H. So that is, again, most often how sort of reactions are displayed to you in terms of endothermic or exothermic. They'll give you the delta H value. It's either positive or negative, and that's sort of how you know. Any questions on any of that stuff there? All right, so we're really getting into sort of the effect of temperature on the rate of the reaction. And obviously, as you may imagine, if you increase the temperature, usually it will increase the rate of the reaction. And really in a reaction, right, everybody's got to climb this hill, right, to get to the other side. So everybody's got to climb that activation energy hill. And basically, when you raise the temperature, you're now going to get probably a greater proportion of molecules that will have enough energy to get up and over to the other side. The same thing is true if you sort of do the opposite, as we'll see. You know, if you lower the temperature, you're essentially removing a lot of energy from that system, and now you're going to have a lot less molecules that have enough energy to get up and over to the other side. That's going to in turn really slow down the rate of your reaction, as opposed to obviously when you increase the temperature, you'll get more people to the other side, and that will increase it. So the Arrhenius relationship here, our equation, is one version of what we look at in relationship to temperature and the rate of a reaction. This is a version of it, although we don't necessarily use this version all that much, but this is our rate constant. A is the frequency factor, and the frequency factor is essentially that proportion of molecules that does have enough energy really to get to the other side. E of A is our activation energy. R is our gas constant. It is actually the one that is using energy, so it is not the one that you use in the ideal gas solid, but this is the 8.314 version of it that has energy unit in it of joules. And temperature is obviously in Kelvin here, definitely in this case. So when we see that energy barrier, which is that activation energy, we get that activated complex there at the transition state. And as I mentioned, what's sort of happening as they are kind of going from reactants up that hill to the transition state, they are starting to really break bonds, right? And they're also starting to also make bonds as well. So they're in that sort of process of kind of breaking what they had going on and starting to make some new ones. And that's really why, as we talked about, I think last time as well, when we do get to this top where we do have that activated complex at the very top of the energy hill, it's really unstable because you really do have something that is like partially made bonds, partially broken bonds. So that's not a really stable situation. It wants to really fix that in a sense. It wants to get rid of the bonds that it's trying to break and make those new bonds. So that's again why, as I mentioned last time, it's very hard sometimes in reactions to isolate what's at the very top of the hill because it does not stay around a very long time because of that situation. And here we can see in this particular case, we have this molecule here is going to basically rearrange. So they're going to basically just kind of swap places. So they do have to kind of break bonds to do that. And what happens is as it's going up, we start to see the bonds here between nitrogen and carbon start to break. And we also starting to get some new bonds forming as we come up to the top. And again, it's going to sort of drop down pretty quickly in this case because of that. So even something in terms of it just rearranging, bless you, you will have this internal breaking and making of bonds that's happening in this type of reaction. And again, the frequency is the number of molecules that begin to form this activated complex in a period of time is essentially, again, the amount of guys that have enough to kind of get up and over that hill. Now, that equation that we just saw, which is the Arrhenius equation, is most often used in this version. So if you kind of go through that top equation there, or the one we saw on the previous page, and you sort of natural log everybody, we get this equation here, which is one that we use a lot for the Arrhenius equation. You can definitely still use this one if you want. But the relationship we see in terms of the rate constant and temperature on this particular graph is also important. what we see is at a lower temperature, we have a much smaller rate constant. And remember, the rate constant is sort of how fast or slow the reaction is going to take place. So if we sort of increase the temperature, we could see a fairly larger there rate constant that's happening. And again, that's due to the input of energy that's going to happen with that temperature increase. This equation here is actually also, much like everything in kinetics, in the form of a straight line. This is y is equal to mx plus b. So this relationship, and why we use it a lot more than, say, maybe the top one, is it will give us that linear relationship that we like to see sort of in graphs and kinetics. And you actually can make a plot, which is usually the Arrhenius plot, and you can see from here, on the y, we would have the natural log of k. On the x here, it would be 1 over the temperature. That does need to be in Kelvin when you do this plot. This will yield you a straight line plot with a negative sloping line. And you could also see from this relationship that the slope of that line is actually going to equal minus E of A over R. So graphically, and why we kind of use this version of the equation, and really this version of the Arrhenius equation is used for sort of graphical purposes to find things like the activation energy. So you can actually make an Arrhenius plot. You could take the slope, and you pretty much can calculate the activation energy for that reaction because R is a constant. You basically just multiply the slope by R, and you would have your activation energy. Now, the slope of this line here, right, is a negatively sloping line, which means the slope value will be negative, and this negative will turn my activation energy into a positive number. And activation energy should always be a positive number, as you can see from those diagrams. The activation energy hill is being put in there. So it is a positive value when you calculate activation energy. And again, you don't want to mess up the sign there. So you actually need to multiply by negative R to the other side so that you get the activation energy. Any questions on that there? And here's a much prettier plot of it here. And again, you could use that slope there to equal your activation energy or calculate your activation energy. Also, another very important sort of relationship that we get graphically from here is this part of it. And the y-intercept, which is what b equals, the natural log of a. So you could actually calculate the frequency factor also through this graphical means. Again, that's obviously where the line will cross the y, right, in this particular case. So by taking the y-intercept and basically taking e to the y-intercept, right, that will get you basically the frequency factor. The units usually associated with the frequency factor are usually the same units as K. So whatever the units of K were are usually the units you have there. By the way, when you kind of do the natural log of K here on this, the units go away. When you take the E back of it, the units come back. So basically, so that's where sort of the units come for the frequency factor in this particular case. Usually it will have the exact same units as the rate constant. So as I mentioned before, the extra energy comes from converting kinetic energy, motion to potential energy. And again, overall, like we talked about, what you essentially get is if we increase the temperature, we are going to get a greater proportion of molecules able to get to the other side. And obviously vice versa. If you lower it, it would get less, either increasing or decreasing the rate, depending if you increase or decrease the temperature. As we talked about at the beginning, if you kind of just bump up the temperature about 10 degrees Celsius, you usually, a lot of reactions can just double the rate of reaction. It'll occur twice as fast. So that's usually a general rule that you follow. And that's what we see here. We look at this graph between the fraction of molecules that basically can get up and over to the other side of our activation energy. We can see at the first temperature, which is the lower temperature, we really only have about that much molecules that can basically get up and over to the other side. Here, when we go to our second temperature, which is T2, we actually will have that much molecules. So as you can see, a much greater proportion of molecules at the higher temperature will be able to get up and over to the other side. So let's take a look and sort of see how we could calculate some of the information from a graph. So for example, this would be typical information that you may be given in a problem. I'll be honest with you, you probably would be given this in Celsius a lot of times as well. So we know obviously temperature in Kelvin, temperature in Celsius plus 273 to convert it. But you'll be given some temperature and rate constant values. And basically what you would need to do is, in this case, in this column, take basically 1 over the temperature for everybody that's in Kelvin. And for this column here, you would need to do the natural log of K. You then would do obviously an XY scatter plot and do a best fit line and actually get the equation for it. There may be some homework problems where you'll need to do that in this chapter for kinetics. You may have to open up Excel, make some graphs, and get some equations, just so you know. So that is very common as well in this kinetics chapter. So if you did that, obviously you would get a graph such as this. And what we wanted from this information, and why don't you take a moment and do it, we want to calculate what is the activation energy and what is the frequency factor here. Okay, so let's take a look and see. So once again, remember our slope of this line here is going to equal minus E of A over R. So we obviously can use that to get to our activation energy, which is what we're looking for. Obviously, we'll take our slope, which is this front number here. We also, again, need the negative in this case to make sure that we do end up with a positive value for our activation energy. So it's going to be negative 1.12 times 10 to the 4. It's going to equal minus our E of A over our R, 8.314 joules per Kelvin per mole. We're going to multiply this to the other side again, also with the negative to the other side. And that will get you an E of A, 93116.8. These are joules, right? Joules per mole if you want. We could divide it into by 1,000, which would get us 1, 2, 3, about 93.1 kilojoules. Again, activation energy is usually given in kilojoules per mole in this particular case. First off, any questions on that there? We can also, as I mentioned earlier, use this to equal our find our frequency factor. I'll spit that out, I think. And again, in this case, our y-intercept will equal the natural log of A here in this case. So in this case, that right there would be our y-intercept. And I'll go over here. I think 26.8 equals the natural log of A. Again, we're going to basically E both sides there. And if we do that, my calculator turns on, maybe. So maybe we should do it again. Make sure it's the right number. We'll do that. And 26.8. Something like 4.36 times 10 to 11. Once again, as I mentioned before, the units of that is usually ends up being the same as what you see for the rate constant. So the units that we would put on that would be reciprocal 1 over molarity seconds. This particular case. Any questions on any of that? So this is really sort of the graphical version of the Arrhenius equation, which is used obviously usually for graphing purposes. Obviously on an exam or quiz, you wouldn't be asked to graph it by hand, but you may be given the graph and need to be able to get the information from it. Yeah. Unless I'm really mad at you and just bring you a graph paper until you start graphing things, right? But any questions on that there? All right. do an old school test. Just bring some graph paper, some rulers, see how it goes. All right, but nobody wants to make graphs. So if you actually know 2 points along that line, technically on that graph, you could actually use what is sometimes referred to as the 2-point version of the Arrhenius equation, where you can basically plug 2 points that are technically on that straight line in that graph that we just saw there. And there are several, just so you know, there are several different versions of this equation. We're going to go with this one. I think your lab manual actually uses a slightly different one as well. And there's one where on the right-hand side, kind of the denominator there is combined as well. So there's kind of 3 different versions of the equation. And some will have, based on what's inside here, some may have a negative on the outside because of what's on the inside, how it's arranged, and some won't. So I would say just go with this one, and trust me when I tell you it will work in any of those situations, but you will see sometimes some different versions of this equation, and it really has to do with sort of what's going on in the parentheses as to what kind of looks like out here. So that's sort of where they're sometimes different. But this, again, is, like I said, an equation that you could use when you have basically 2 points from that line, or you're just kind of given 2 points that technically would be on that line, and you don't want to obviously make the graph. So this is a rate constant at temperature 2. Right. That's the rate constant at temperature 1 equals our activation energy. That is still the same R we just used, which is our 8.314 version of it. These are obviously our 2 temperatures at which we got our rate constants going on. They obviously need to be in Kelvin as well, so that everything cancels out. Now, speaking of units, you do need to be really careful, and it is a place where people make a lot of mistakes on this equation, is this part of it, the E of A over R. Again, E of A is typically given to you in kilojoules. R, as you can see, there is in joules. So you do need to do a conversion of units between those so everything properly cancels out. Otherwise, you're going to be off right by a factor like 1,000 in that situation. It really doesn't matter which one you want to do. You could either convert the R into kilojoules, you can convert the activation energy into joules, but you do have to do some type of conversion so that you don't mess that up. I would say the second thing that people mess up most on this equation is this part. They leave it at temperature in Celsius. So again, it does also need to be in Kelvin for sure when you're doing that. And a way to remember that is right there, right? So the R has Kelvin in it. So that should hopefully be a reminder that you need to do that. This will allow you, again, if you, for example, know the 2 rate constants and 1 temperature, you can figure out the temperature of the other rate constant. If you know 2 temperatures and 1 rate constant, you can figure out the rate constant at the other temperature. If you know 2 rate constants and 2 temperatures, you can figure out the activation energy as well. So there's a lot of different things that you can sort of calculate from this formula. Rate constants, temperatures, or activation energies are very common things. Pretty much everything here can be solved for basically in this equation. So why don't we solve for something here? So in this case, we're going to look for the activation energy here in a reaction where we have a rate constant of 2.57 at 701 Kelvin and 567 at 895 Kelvin. What is the activation energy? So take a few moments. Okay, so let's take a look. So in this case, we got a rate constant here, 2.57. We got a temperature that goes with it of 701 Kelvin. We have another rate constant of 567 and a temperature that goes with that, which is 895 Kelvin. Doesn't matter which one I call K1 and K2. The answer is really it doesn't, as long as you keep the appropriate temperature together with it. So whichever one you call K1 should have the appropriate temperature as T1 and vice versa. In this case, we're looking for E of A, and that means perhaps we should go with our equation here. Our K2 over K1 equals our E of A over R, 1 over T1 minus 1 over T2. In this case, our temperatures are in Kelvin, so we're good to go on that. So we can plug this in. Natural log of, looks like 567 over 2.57 equals our E of A. R is our constant, 8.314 joules per Kelvin per mole. our 1 over our first temperature, which is already in Kelvin, so that's good, and our second there, which is also in Kelvin. So just to clean up, I'm going to clean up here the left-hand side, I think. So remember, you actually do want to divide first before you do the natural log. So it's going to be 567 divided by 2.57. Then you're going to take a little natural log of it, and that's going to give you something like 5.39645 equals our E of A over 8.314. I'm going to kind of clean up what we got going on in there. I'm going to take 1 divided by 701 minus 1 divided by 895. And that's going to get me something like 3.092 times 10 to the minus 4. I'm going to multiply that to the other side, and then I'm going to divide that other guy. So that gets divided, not multiplied. So we're going to do 5.39. Oops. Gonna do a calculator that just died on me. And, oh, gotta go to reserve. Let's see if we can find a calculator. I'm gonna run out of fingers, I think. Let's see. Let's try that one. Maybe that'll work. Let's see if this got batteries. I left my real calculator somewhere. I'm gonna find it eventually this week, I suppose. I don't know. I'm like, where did it go? All right, so we're gonna go 5.39645 times 8.314, and again, where that's gonna get us something maybe like 44.866 is equal to E of A 3.092 times 10 to the minus 4. We're then going to divide that to the other side, like I was saying earlier. And now I remember why I don't like this calculator, because you can't really read what it says, but we'll try it here. Exponent negative 4. There you go. Maybe. That will then get you an E of A of, we'll go 145, 103.76. These are joules again. They are joules based off of obviously this guy here. And usually it is kilojoules. So we'll move that a few places that way, divided by 1,000, about 145 kilojoules. Again, should be a positive number when it's all said and done. Any questions on that there? I would say probably in terms of the Arrhenius equation, this is probably the one that you'd use the most, followed by sort of the graphical version of it. So most of the time, you're probably going to plug and chug it to this equation to get it. Any questions on that there? All right, let's take a look at another one here. We got a... all right, let's try this one here. Let's said the rate of the reaction is doubled for every 10-degree temperature rise. Calculate the activation energy in this case. Let's actually do a different one. Let's just make one up here. Why not? That sounds like fun, maybe. Let's say we had a rate constant at 45 degrees Celsius. That was 4.56 reciprocal seconds. At what temperature would the rate constant be? We'll go with 25.5 reciprocal seconds. If the activation energy is, I don't know, we'll do 125 kilojoules. I think that's hopefully everything you need. Hopefully, let's see. There you go. There we go. All right, so what's temperature in degrees Celsius? We'll do it. Give it a go. I'll do it as well, because couple seconds. We're looking for a second temperature, and we have a K value that goes with that guy, which is 25.5. And we have the activation energy here, which is 125 kilojoules. So we do need to do a little bit of conversions here as I'm on to my third calculator of the evening. We got 318. So we do need to convert that again into Kelvin. Need to add a 273, right, to do that. Other than that, everything else is probably fairly okay. We're going to go our natural log of our K2 over K1 equals E of A over R. 1 over T1 minus 1 over T2, putting in our numbers that we got. I went with the larger one on top there, and we got 4.56 equals our E of A, which is our 125 kilojoules. I am personally going to multiply by 1,000, and again, the purpose of that is to convert it into joules. So it is in the right units for my R value, which is in joules. Once again, if you want to go kilojoules on both of them, you can do that as well. It should come out the same. We're going to divide by our 1 over our temperature there, which was 318, minus 1 over our temperature we're looking to find. All right, so we'll do some cleanup here. We'll clean up the left-hand side, hopefully, on this calculator. Let's see, 25.5 divided by 4.56. A little natural log action of it there. Looks like 1.721355, we'll call it. I'm going to also clean up here. So I'm going to go 125 times 1,000 divided by 8.314. That's going to get me here a lot of numbers. 15034.880. 1 over 318 minus 1 over T. At this point, we need to divide that to the other side. So we're going to go 1.721355 divided by 15034.880. That's going to get us here 0.000114449 equals 1 over 318 minus 1 over T2. At this point, I'm going to actually add this to the other side while I am basically subtracting this to the other side. We're going to kind of switch places with each of those. So that will give me basically 1 over T2 is equal to basically 1 over 318 minus 0.000114449. All right, so clean up the right-hand side at this point. 1 divided by 318 minus our 0.000114449. Gonna give us 1 over T2 is equal to 0.003030164. Remember, this is not the temperature, it is 1 over the temperature, right? So basically, temperature 2 would equal 1 over that number there, right? If I take 1 divided by that number, maybe, let's see here. I will equal, dare I say, 330. Let's go up here. 330, and this obviously would be Kelvin based off of that guy there, minus a 273 to get us back to Celsius. Not too bad for making up numbers, I suppose. 57 degrees Celsius, that seems good. Question on that there. We do see what we talked about, right? At 45 degrees, we had a rate constant of 4.56. We raised the temperature here 12 degrees. Rate constant definitely went up more than double, right? It went up to like 25 or so, even with making up numbers, yes. Who has to convert what to joules at the end? Are you talking about over here, or like just wait to the end to do it? You might be off because especially doing the 1 over and all that. So it's probably best just to kind of get everybody in the right units to begin with, especially also if you have something where you may have to do like a natural log or an E and stuff like that. So that also will affect it, especially if you're doing like an E or something like that, if the number just slightly different. Even with a round, you'll sometimes get a pretty big difference in terms of numbers. So I would definitely do it at the beginning. Sure. Yeah. Other questions? All right. So again, that's the Arrhenius equation, kind of the 2-point version, to see how the temperature affects the rate constant, or again, like I said, activation energy and so forth. Any questions on that? All right. So the next thing we're going to talk about is, and really the last thing in this chapter, is what is known as reaction mechanisms. So just a reminder that not all reactions really take place in a sort of one-step process. So if I had a reaction A plus B that goes to E plus F, this may not occur in like a one-step sort of fashion. It may actually be multiple individual sort of steps that occur to kind of get us there. So for example, you may have like A plus B goes to C plus D, then maybe C plus D goes to E plus F. I know my alphabet, that's pretty good. When we add equations together, a reminder that anything on opposite sides of the arrows can cancel or reduce. So in this case, the C and the C would cancel, the D and the D would cancel. Everybody that's on the left-hand side of the arrow will stay there. So that's A plus B. Everybody on the right-hand side of the arrow will stay there as well, E plus F. And that gives us our overall reaction. This is very similar to everybody's favorite thing, which was like Hess's law, perhaps, right? When you use all those individual equations to kind of build out an old equation, an overall equation. So for example, here in this reaction, when we have 2NO plus some O2 makes NO2, during the process of this reaction, N2O2 is detected, but we could clearly see in the overall reaction, it is not present anywhere. So what this would imply is that this reaction is probably a multi-step sort of reaction that takes place, where somewhere along the way, the N2O2 is produced, and also somewhere along the way it is then sort of used up, and that would explain it. So one possible explanation of how this mechanism or this reaction takes place is to use what are referred to as elementary steps. And elementary steps are, our elementary reactions are basically the kind of individual reactions that when you put them together, gives you the overall reaction that you're looking for. So it's kind of like when you're building your overall reaction from. So possibly what could happen is maybe these two NOs make that N2O2, which is why maybe it was detected. And the next step, it is then used to make our products, which is why it's not there in the overall reaction. The N2O2 would be considered an intermediate in this case, as it gets used up in this reaction and not present in the overall reaction. Now, an intermediate, as I just mentioned, which the N2O2 would be in this case, is a species that's actually made early on in a mechanism and then used up completely by the time it's over. Again, it should not appear in the actual overall reaction. So when we talk about the reaction taking place, there's the molecularity of the reactions. Some reactions are elementary steps that have one molecule reacting, which is known as unimolecular. Some elementary steps will have two reacting, which are bimolecular, and termolecular would have three. So in each of these cases, these both have two molecules reacting in each of these elementary steps. They both would be bimolecular in this case because they both have those two reactant molecules basically reacting. Now, when we're dealing with elementary steps and when we're dealing with mechanisms, this is actually the only place where you can use the coefficients from the balance equation as the orders. And this is the only place where you can kind of do that in kinetics. So if you had an elementary step that was unimolecular, you could write a rate law based off of the reactant, and it would be the rates equal to K times A. If it was bimolecular, you could do the same thing. You could write a rate law for that elementary step that rates equal to K times A times B. And this is basically 2A, right? And that is where that 2 comes from. That is basically the coefficient. And the rate is equal to K times A to the 2. So you could, for these elementary steps in mechanisms, which again is the only place you could do this, you can write rate laws for them. Now, what is the purpose of mechanisms and sort of what are we looking for in these type of problems? The idea of mechanisms is it is a plausible sort of explanation of how this reaction could take place. Does it mean that is always how that reaction may take place? No, but it's sort of a logical idea of how it may take place. So, how do you know if this mechanism is a sort of good mechanism or a bad mechanism for a particular reaction? There's really kind of two things that you have to look at to make sure that it is a good or sort of bad mechanism. The first thing is when you add up all the elementary steps in that sort of mechanism, it does need to give you the reaction you're looking at for. So it needs to add up to basically the reaction that you're looking at. Obviously, if the reactions don't add up to the equation you're trying to solve for, it is not a great mechanism because it doesn't give you the reaction you need. The second thing is the rate determining step. And the rate determining step is sometimes abbreviated as the RDS, or the rate determining step, should have a rate law that is the same rate law that you find experimentally. So as we know, rate laws are found experimentally, but in a mechanism, there should be a step, which is the rate determining step, that should have a rate law that actually matches the one that was found experimentally. And then you would know it's sort of a good reaction in a sense. What is the rate determining step? The rate determining step is actually the slowest step in the mechanism. It is the one that basically determines how fast or slow that reaction is going to take place. It's like when you're at the market and you're in the 10 items or less line, the guy in front of you has 400 items, right? So you're never going to get through that until they're done with their 400 items. That is your rate determining step to getting out of the supermarket, right? So the rate determining step by our turtle here, slow moving as we go through there. So let's take a look at a couple of things here. We want to know, for example, that the experimental rate law for this reaction was found to be the rate is equal to K times the concentration of NO2 squared. The reaction is believed to occur in these steps here. Why don't you take a moment, see if you can answer these questions. We want to know what is the overall reaction. We want to know what is the intermediates in this reaction, and what can we say about the rates of 1 and 2. So take a few moments there to see what you come up with for some of these, and we'll talk about it. So first off, we want the equation of the overall reaction. So this is a two-step mechanism. So we're basically, to get the overall equation, we're just going to add them together. So in this case, looking on the left here and the right, these guys should cancel. That guy there should also. And that's going to leave us here NO2 plus CO goes to NO plus CO2. Any questions on that there? That would mean the intermediates are, in this case, what is it? NO3? Is there any other intermediate here? Is NO2 an intermediate? It is actually not an intermediate because it actually does appear in the overall reaction. So remember that an intermediate should not really appear in the overall reaction. In this case, we just kind of reduced it down, but it's still there at the end. So even though we did reduce it down, NO2 in this case would not be an intermediate. In this case, it would just be the NO3. Any questions on that there? Now, because this is a mechanism and because of that, we can actually use these elementary steps, and we can actually write rate laws for each of these elementary steps, again, using the coefficients as the orders. And once again, that's the only place you could actually do that. And in this case, for the first step, the rate would equal K times NO2, and it would be squared again, because basically that is 2NO2 in this case, right, when you put them together. In this case, we could also write a rate law for the second elementary step, which would be K times NO3 and CO. Now, first off, any questions on how to get those there? Now, in this case, they also gave us that the experimentally found rate law, right, was that the rate is equal to KNO2 squared in this case. So what we know is when we look at the mechanism and we look at the rate laws for the mechanisms and the different steps, and we look at the rate law there experimentally, which step should be my rate determining step in this case? So the rate law that was found experimentally is this, and the rate determining step should have the exact same rate law as the one that is found in experimentally, right? So which one has the exact same rate law? It is the first one. So because they have a matching rate law, we know that step one in this mechanism is actually the slow step in this mechanism. This is actually the rate determining step, the slow step in this mechanism. And by knowing that, we know that step one in this case, right, should be slower, right, than step two in this case. Step two should definitely be faster. Any questions on that there? So this is one type of mechanism problem where, again, you could get, as we did here, we could figure out the overall reaction. We could figure out any intermediates there are. We could actually figure out which step is the rate determining step. Now, there are some other mechanism problems where they will sort of tell you what the rate determining step, or you need to kind of figure out the rate determining step. And what you need to do after you do that is then figure out, is this kind of like a good or bad mechanism, essentially? Like that's sort of the idea. I sort of think of it like math, like proofs, like you have the answer, but you got to prove it kind of thing. So you got to kind of prove if it's kind of a good or bad mechanism. So you do need to sort of figure out in those type of problems, sort of what is the rate determining step? Is it a good or bad mechanism? So it's a really hard way to determine which one's the rate determining step in this type of problem. And the hard way is it pretty much says slow next to it. So that's how you know it is, right? So not too hard to figure out. So in this reaction, we have a three-step mechanism, and experimentally, the rate here was found to be K times H2 and NO squared in this case. And we have this reaction of 2H2 plus 2NO goes to 2H2O plus some N2 in this particular case. So just borrow some of that there, actually. All right. So first off, we can know based on what is given here that this is the rate determining step. And in order for this reaction to be good, do you want to talk? Oh, you good? Oh yeah, go ahead. You want to talk? Yeah, go ahead. I'll stop. Yeah, no problem.